So all that crazy stuff we're talking about with orbitals is actually related to the properties we see on the periodic table. Quantum mechanical theory describes behavior of electrons. The electrons are found within orbitals, right? And we can describe the orbital by a series of quantum numbers, but we can also use a shorthand called electron configuration. So if we look at hydrogen, hydrogen has one electron. The lowest energy is where it's going to be. So n equals 1, that first principal energy level is going to be the lowest. In that energy level, there's only one orbital. It's the s orbital. So there's one s, and each orbital can hold 2 electrons. There's only 1 electron here, so we put a superscript of 1 to tell us there's 1 electron in the 1s orbital. And this is the electron configuration for hydrogen. So if we go to the crazy hotel analogy, I should probably give that a name. I'll have to think of something clever. The electron configurations are like the shorthand notation that the desk clerk has because he needs to keep track of who's in which room, so he doesn't give keys to a room to somebody when there's already somebody staying there, right? So this is just like a little list of where are the electrons. That's all an electron configuration is. So how do these electrons occupy orbitals? They're going to go for the lowest energy. We do calculations with Schrodinger's equation, and we find out that the 1 electron in hydrogen occupies the lowest energy orbital. And we can do these calculations for hydrogen because it only has 1 electron. When you get to multi-electron atoms, which is everything but hydrogen, we can't exactly solve Schrodinger's equation. And that's because there are interactions between electrons within the atom. So that really complicates the equation. But if we do approximate solutions, we find that the orbitals are hydrogen-like. So they're very similar to the orbitals in hydrogen. The important concept about these multi-electron atoms is that we need to deal with the electron spin, and we also have what's called energy splitting of the sublevels. So orbital diagrams are another way to represent where the electrons are, and this allows us to indicate the spin of the electrons. So for hydrogen, we use boxes in orbital diagrams, and each box represents an orbital. So each box is like a bed in the hotel, and here's a person sleeping in the bed. So we use half arrows to represent each electron, and that spin, these electrons, the arrows, are either up or down. So just by convention, we say if the spin is up, it's positive, and if it's down, it's negative. And if you look at a bunch of hydrogen atoms, you would find that about half of them are spin up and about half of them are spin down. The Pauli exclusion principle is named after a scientist whose last name was Pauli, says that no 2 electrons in an atom can have the same 4 quantum numbers. There's 4 quantum numbers. We've talked mostly about the first 3. That last one, the spin, is what allows us to have 2 electrons in the same orbital, but their spins have to be opposite. So you can have 2 electrons in the same orbital. They're going to have n, l, and m sub l be the same, but the 4th quantum number has to be different. Bottom line here is each orbital can have a maximum of only 2 electrons with opposing spins. So that's important. So in the hotel, 2 people per bed, opposite sexes. Oh, there's another typo. Knowing the number of orbitals in a sublevel allows us to determine the maximum number of electrons in the sublevel. So the S sublevel has 1 orbital. It can hold 2 electrons. The P sublevel, remember there were 3 different orbitals, and they were just oriented differently in space. Each orbital holds 2 electrons, so the p sublevel can hold 6 electrons. The d sublevel has 5 orbitals. The d room in the hotel has 5 beds. It can hold 10 people. Okay? F is 7 orbitals, 14 electrons. So let's look at helium. So the electron configuration for helium is 1s2. And that tells us in principal energy level 1, in the s orbital, there are 2 electrons. The orbital diagram would look like this. Here's the box for the 1s orbital, and we have 1 electron with spin up and 1 with spin down. And here are the quantum numbers for those 2 electrons. They both are quantum principal level 1, and the angular momentum is 0, and m sub L, the magnetic one, is 0, and the spin quantum number, one of them is plus 1/2 and one is minus 1/2. Because no 2 electrons can have exactly the same quantum numbers. There's 4 numbers, and at least one of them has to be different. So any questions? You said it wasn't as weird. I'm not drawing strange pictures. Just little boxes with arrows. That's not as weird as those F orbitals. Hydrogen is nice and simple. In the sublevels of hydrogen, all the sublevels in a principal energy level, remember the principal energy is like the floor in the hotel. All the rooms on the same floor have the same price, the same amount of energy. So on the second floor where there's s orbitals and p orbitals, they're all the same price. That's only true in hydrogen. In all the other atoms, there's interactions between elements, and so the p rooms are a little more expensive than the s rooms because of those noisy people coming up the elevator. So for hydrogen, the orbital energy depends only on n, and we say that orbitals with the same energy are degenerate. So they're degenerate, meaning they have the same amount of energy. But when we get to the multielectron atoms, the energies of the sublevels are split. And it's caused by charge interactions between the electrons, by shielding. The inner electrons shield the outer ones from the nucleus, and also by penetration. Some of the orbitals penetrate closer to the nucleus than others. It's kind of complicated. Bottom line, in general, within a principal energy level, we have this order. So like, what would n be for the first level that can have an F sublevel? 4. The first n equals 1 only has S, n equals 2 has S and P, n equals 3 has S, P, D, and F, n equals 4 has F. So n equals 4, within n equals 4, the S is lower in energy than the P, which is lower than the D, which is lower than the F. The F has the highest energy within the principal level. So on the 4th floor of the hotel, the S room is closest to the elevator, it's the cheapest. The F room is farthest from the elevator, it's the most expensive. And that's true on that floor. Then we have to talk about charge interactions. Coulomb's law, again, with the physics. Coulomb's law states that the potential energy of 2 charged particles depends on their charges, Q1 and Q2, and on their separation, which is R, so the distance between them. So this is a constant that we don't really care about, but the energy is equal to this constant times Q1 times Q2 divided by R. So if these particles have larger charges, the interaction or the potential energy between them will be greater. If the distance between them is smaller, the potential energy would be greater. If you have like charges, E is positive. Like charges repel each other. They push away. You can think about this a lot like magnets. Electrical interactions are not the same as magnetic interactions, but they're very similar. Like charges repel opposite charges. E is negative and the charges attract. So think about a north pole and a south pole of a magnet, and they will stick together, right? But if you take two south poles, you can try to push them together, but they do not want to go together. If you have stronger magnets, we've got those Sonicare toothbrushes, and after the brush part wears out, you take them apart, and there's some really strong magnets in there. And of course, the kids like to harvest the magnets, and they take the hard drives apart, and there's really neat magnets in there too. A lot stronger than just little refrigerator magnets. And if you've got those really strong magnets, they'll go whack together. I mean, just really strong, because the charge, the magnetic charge on those is greater, and so the force of attraction is greater. And also the potential energy depends on the distance. And if you've ever, I don't know, my refrigerator is always covered with paper stuck up with magnets, right? And sometimes you run out of magnets, and so you're sticking multiple pieces of paper up with the same magnet. And there comes a point where it won't hold up anymore, because the distance between the door of the refrigerator and the magnet has gotten great enough that it cannot hold together anymore. Magnets are very sensitive to the distance, and so are electrical charges. So the strength of the interaction increases when the size of the charges is greater and when the distance is smaller. And these are things that if you've ever played with magnets, and I've not met a person yet who hasn't, if you think about it for a little while, you already know this. Opposites attract, and the attraction is stronger if the magnets are stronger and if the magnets are closer together. Well, what happens in a multi-electron atom is that each electron feels an attraction to the nucleus and a repulsion from the other electrons. Because electrons are negative, and two negative electrons are going to repel each other. The nucleus is positive, and that is attracting the electrons. The repulsions cause the electron to have a net reduced attraction to the nucleus. We say it's shielded from the nucleus. And so the total amount of attraction that an electron feels for the nucleus is called the effective nuclear charge of the electron. And the symbol they use for that is ZF, EFF. So Z effective, the effective nuclear charge. So that has to do with the magnitude of the charges. And then penetration has to do with how close does the electron get to the nucleus. The closer the electron is to the nucleus, the more attraction it experiences. So if an outer electron is good at penetrating the electron cloud of the inner electrons, it will have more attraction for the nucleus. The degree of penetration is related to the orbital's radial distribution function, those funky, curvy graph things we saw earlier. So let's look at a picture. 3+ charge on the nucleus. What element is that? Just the nucleus with 3 protons. Lithium. So this is lithium. So lithium has 3 protons and it's got 3 electrons. And so here we have 2 electrons here, and this electron, when it's out here, experiences a net charge of about +1. Because these guys are repelling it. Another way to think about it, which works a lot better for me, is think about them kind of canceling out. So here we've got a +3 charge and there's a -1, and there's a -1, and those balance out 2 of the plus charges here. And so this experiences about a +1 charge. So the attraction of this electron out here to the nucleus is less than if it were in closer. And that's the shielding. These electrons that are closer shield this electron from the nucleus. I'm getting all sorts of strange analogy ideas, but I'm not sure I want to let them come out. Here, if this electron is able to penetrate closer to the nucleus, now it is not subject to shielding by these guys, and so it's going to experience the full +3 charge of the nucleus. And so this is going to be more strongly attracted. So penetration of the orbital, if the electron can get in closer to the nucleus, will increase the amount of attraction. And shielding of the other electrons that are closer will cause this to have a decreased attraction, decreased energy.
Is this the basis of ions then?
Of what?
Are ions then? Are they losing
Somewhat, yes. This electron on the outside is experiencing less attraction for the nucleus, so it's the electron on the outside that's going to be lost when it becomes an ion. So the 2s orbital penetrates more deeply into the 1s orbital than the 2p orbital does. Okay, so let's try to make some sense out of this graph. Okay, so here's the 1s orbital, and we're just chopping it off because it goes way, way up here. We don't need to look at that. The 2p orbital comes in like this, right? And so it overlaps a little bit, but the 2s orbital has this node in here, and then it's got this bump in here. And so this region here gets much closer to the nucleus than the p orbital does. So the p orbitals are more shielded from the attractive force of the nucleus. The 2s orbital then is going to be lower in energy than the 2p orbitals, because it has more attraction to the nucleus. So because of penetration, the sublevels of each principal level are not degenerate for elements other than hydrogen, which is, the majority of the elements, right? We only talk about hydrogen so much because he's so simple and easier to talk about. As you get up into the 4th and 5th principal levels, the effects of penetration become even more important. And so the 4s orbital lies lower in energy than the 3d orbitals, and 5s is lower than 4d. And the energy separation between one set of orbitals and the next becomes smaller and smaller. The relative energy ordering can actually vary among the elements. So we're going to tell you that that's possible, and we're going to try not to go there. So, all of that being said, let's look at this. So if we look at, say, n equals 4, and we compare 4s, 4p, and 4d, there is this trend, s, p, d, as you go s, p, d, f, g, h, i, the energy will increase. If this was hydrogen and these were degenerate, the 4s, the 4p's, and the 4d's would all be at the same level. They are not, because of penetration and shielding of the inner electrons. There's interactions between the electrons. So this is the order that we end up with. And these orbitals will be filled from the lowest energy to the highest energy. So 1s is lowest, and then 2s, and then the 2p sublevel, and then 3s, and 3p, and everything's all nice until you get to that point. But the 4s is lower in energy than the 3d. So it goes 4s, 3d, 4p, 5s, 4d. You're like, oh my goodness, what a jumbled up mess. It looks like a mess. There's patterns though, and we'll show you how you can remember this without hurting yourself. Any questions about the idea here that these energy levels are kind of wacky like that? How do they measure it? That's a good question. It's complicated. Oh, cop out there. That would be physical chemistry. Yeah. There's a lot of different things they do. It's complicated. Some of it has to do with Schrodinger's equation and solving the wave functions and things. And we can get approximations, but we can't solve it exactly.
So are these all very theoretical concepts that they actually haven't been able to...
Is it all theoretical concepts and we don't really have any concrete proof for this? All the evidence that we have suggests that this theory is correct. Now, could it be proven incorrect at some point in the future? Yes, it could. That's always a possibility, and there's always people out there trying to do that. But, Einstein spent much of his life trying to disprove quantum mechanics, and he couldn't do it. And so I really don't think we're going to be able to disprove this. It does explain so much. It just explains an unbelievable amount of stuff. So orbital filling. The orbitals are going to fill from low energy to high energy. So, you think about electrons as people going to this hotel, and they're cheap. They're going to go for the cheap room first. So they're going to fill, those rooms are going to fill the cheapest one first, and then the next expensive one. So lower energy orbitals fill before higher energy orbitals. This is the Aufbau principle. Orbitals within the same sublevel are going to have the same energy. So what does that mean? The 3 p orbitals in the sublevel, those have the same energy. In my hotel, those are 3 beds in the same room. You can't really charge more for one bed in a room than you do the other, right? They're all the same. And this is one way to look at the filling order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Nobody likes to memorize that. I'll show you a better way. The orbitals can hold no more than 2 electrons each. That's the Pauli exclusion principle, and the spins are going to be opposite. So in the hotel, you can only have 2 people per bed. So in that 2p room, which is a sub-level, there are 3 beds. Each bed can hold a maximum of 2 people. And Hund's rule tells us that when we're filling degenerate orbitals, so orbitals within the same sublevel, the 3p orbitals or the 7f orbitals, the electrons will fill them singly first with parallel spins. So this is a little bit like the bus. So say you've got 3 people and they're going to share this room that has 3 beds. Are 2 of them going to sleep in a bed together when they could each have their own bed? No, they're each going to take their own bed. Okay? We're leaving romance and any sort of sexual interactions completely out of this. This is a very platonic analogy, okay? So they're gonna fill them singly first. So this is one way that you can remember the order of filling. And some people like this. You start by drawing a diagram, and you've got an energy shell on a row, and then you list the sublevels. So 1s, 2s has 2 of them, 3s has 3, the 4 has 4, the 5 actually has 5, but we're never ever going to go over there. But you fill them up like this, and then to find the order, you draw diagonal lines. So you're going to go like this, and then you jump back up here, and you go here, and then you go there, and there. You get the idea? So it's going to be in order 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. That's one way to do it. So, next exam, you'll have to know the order of orbital filling. Well, you come in, before you rip the periodic table off, write this little table. Because as soon as you look at the exam, you're going to lose your mind, right? And forget everything. Yeah, that's what happens. So you write stuff like this down before you lose your mind. Then after you lost your mind, you can go back and look at it. Oh, look, someone wrote this on my paper for me. I could figure this out now. So that's one way to do it. Just some notes about writing electron configurations. Unless it's stated otherwise, when we say electron configuration, we mean what's called the ground state, the lowest energy configuration. The excited state happens when you zap it with electricity or put energy into it in some way. But unless otherwise stated, we're talking about ground state. The number of electrons in a neutral atom is equal to its atomic number. We've covered that, but don't forget. So like if we're going to do sulfur, sulfur is element number 16. That means it has 16 protons, it has 16 electrons. So we get the number of electrons we have to mess around with from the periodic table. So is anyone curious how you could have two negatively charged electrons in one orbital? They should repel each other, right? They should. But they're going to have opposite spin, so their motion interacts in a way that minimizes the repulsion between them. But you can't have two electrons with the same spin in the same orbital. They'll blow each other away. So they have to have opposite spins. And each orbital can hold a maximum of 2 electrons. So you take the number of orbitals that you have and you multiply by 2 and you get the number of electrons that you can throw in there. So the electron configuration is just a listing of sublevels in the order of filling, and then we list the number of electrons in that level as a subscript. So for krypton, krypton has 36 electrons. And if you add up all the superscripts here, I said subscript, I meant superscript. If you add these up, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36. All of them are accounted for. The superscripts add up to the number of electrons. The number of electrons is written in nice large numbers above the element symbol in the periodic table. So krypton has this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and there's that wacky order there. We have a shorthand for this because this gets kind of tedious when you get up to the bigger elements. It's called a noble gas configuration or an inner electron configuration. And so what we do is we use the symbol of the previous noble gas in brackets to represent all of the inner elements. Inner electrons. So if we look at rubidium, where'd you go? Rubidium, he's in the 5th period, element number 37. 37 electrons. So this is his full electron configuration. But this part is the same as krypton, right? So how about instead of writing all of that, we put krypton symbol in brackets and we just write the stuff that's on top of it. It's faster. It's easier to look at too. So that's the noble gas configuration. It's a shorthand version. You should know how to do both and what both of them mean. Like if you're given an electron configuration and you need to know which element it is, one way to do it is just to add up the superscripts. You get the number of electrons, you find that element on the periodic table, and you're done. Let's look at the orbital diagrams. Here's lithium. Lithium has 3 electrons. So its electron configuration will be 1s2. That's the first level. It's going to be full before it goes on to the second level. And then the 2s orbital is going to have 1 electron in it. So here we have the orbital diagrams. There's 1s and 2s. And this one fills up first, and then this guy has to go to a more expensive room. Here's beryllium, so both of these will be full. There's boron, and so he's going to fill up like this. And what's interesting here is carbon. So carbon, the electrons come in, and 2 of them take the first room, and 2 of them take the second room, and then this third room has 3 beds in it, and there's 2 electrons left, and they're going to sleep in separate beds as long as they can. So they're going to fill up the empty orbitals first with parallel spins, and then the next one that comes in after those are full would have to pair up with an opposite spin. Any questions? So let's write electron configurations for chlorine, silicon, strontium, and oxygen. So chlorine. How many electrons does chlorine have? 17. So chlorine, we got 17 electrons. So we need to be able to remember the order of filling. So it's going to be 1s, 2s, 2p, 3s, 3p, 4s, 3d, and we'll see how far that gets us. So if we have a list of order of filling like that, that's not a 15. That's an S. Okay. So 1s, how many electrons can we put in there? 2. And next is 2s. How many electrons can we put in there? 2. So we're up to 4 now. Next is 2p. How many electrons? 6. So the p subshell has 3 orbitals. 3 times 2, 6. And then we get 3s can hold how many? 2. And 3p, well, 3p can hold 6 electrons, but how many do we have left?
6.
We've got 5 left. 2 plus 2 is 4, plus 6 is 10, plus 2 is 8, and we're going for 17. I'm missing something. 7, yeah. I'm sorry, yeah, 12 plus 5 is 17. Oh my goodness. You might want to use a calculator to do that. That's the electron configuration for chlorine. How many electrons does silicon have? 14. So that's going to be 1s2, 2s2, 2p6. So now we're up to 10 electrons. We've got 4 left. We'll put 2 in the 3s, and then the 3p is going to get 1. Yeah, 2. Just testing you. Not really. Tired. You're tired too. Is this making any sense? Okay, so strontium. How many electrons does strontium have? 38. Oh my goodness. Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How many electrons can the 3d? 10. And I ran out of space. Well, I can fit one more in there. 4p, 6, and then I need 2 more, so they're going to go in the 5s2. All of this is actually hiding in the periodic table. You just saw it?
Yeah.
It's cool, huh?
It is.
It's really cool.
It helps a lot too.
It helps a lot. Okay, so let's do oxygen. Oxygen has 8 electrons. See, I can look at the periodic table and say it's going to end in 2p4. So 1s2, 2s2, there's 4 electrons. And we need 2 more, 2p4. What? Yeah, it's like playing one of those weird games with the dice or something. Okay.